Okay, welcome all. Thank you for coming. The presentation is being filmed and will be made available online within a few days. I would like to thank Silesia for hosting this event. Orbital and BlueTech, as well as Domestic, who helped out at the initial stage, are all part of the Silesia and the Norwegian Center of Expertise for Micro and Nanotechnology. Meeting other innovators and cooperating on projects like this is one of the main advantages to being part of a cluster such as this. We'd also like to thank Innovation Norway and NCE again for supporting this project, for which we are very grateful. We'll start with a couple of short company presentations and then present the project. And by the way, there'll be plenty of time for a Q&A after the presentation, just so you know. Yeah. So my name is Thomas Moss. I'm the CEO of Orbital. We are an industrial inspection RPS or drone company, providing services for both the private and public sector. And it works. We're an RO3 company, which means we have the necessary approvals to perform any kind of aerial operation. And our core services are inspection and photo scanning. Inspection is flight operations for routine control and fault detection with different sensors. And photo scanning entails capturing an entire area and, in essence, creating a 3D model of that area. Those two services essentially produce the same result, giving the client historical data to map changes over time. And from the start, we've been all about the data. Flying aerial systems is the only way to capture that data. And that's what's important to the client, precise data. Of course, it also helps that our way of collecting that data is faster, more accurate, safer, and more cost efficient. Another dream from our client's perspective is objective data. Two inspectors can and often will have differing opinions on the same problem, damage, or issue, and that's where this project comes in. What if we could train computers to do the evaluations? Because you have to start somewhere, and because this is of interest for our clients and partners, we started with rust detection. But of course, as you will see, this method could be used to detect nearly anything. With that, I hand you over to Stian Broen, CEO of BlueTech. Thank you.
Thank you very much, Thomas. Yes, as Thomas said, my name is Stian Broen. I am the CEO of BlueTech Solutions. So very nice to see all of you here today. We are extremely excited about this project. So we look very much forward to showing everybody what we did. I will just very briefly tell about our company. So to put context correctly to this. So what's our thing? We work with the Internet of Things. And our product is an online service for authenticating devices, collecting data, visualize data, and also analyze data. So that's our product basically. But we work also a lot in the consultancy space, where we have cases and projects with partners and customers, where the projects are related to either one of those four or all of them. And that's basically the reason why we feel like we are the natural partner for Orbital in this project. So just a little bit about what's the deal here. Yeah. So we are a knowledge-driven company. All of our value is in what we know and what we can do. And we also have done an important realization, and that is in that we can never stop learning. If the moment we do it, we will fall behind. So we are relentlessly learning new stuff. And we focus on the full stack of IoT, which means that we have to be experts in all of these disciplines. And the core thing is, of course, that we want our customer to succeed in the IoT space. And that involves a lot of businesses and markets. And the point of it all is basically summed up in this one. So we are walking the way from the bottom here on all the way to the top, where you have all the data being gathered at the bottom, and on the top you have basically extracted the essence of it, which is the most valuable thing, and that is the wisdom, the knowledge about what's actually going on, what are the complications, what are the results, how can we predict the outcome in the future, and those things. Internet of Things market opportunity, I will not say too much about it because it's a matter of Googling it and you will find a lot of reports on that. The point is that it's enormous. That's what I was going to say about our company very briefly, and I will let Luca Petrica, which is Chief Technology Officer, do the presentation on project.
Thank you. Hello and welcome. So here now I'm Luca and I'm CTO of the BlueTech. So here now during this presentation we'll go a little bit into the project. We'll see what we did and how we did it. So before we start, how many of you have technical background, more or less? Know something about technical? Okay, good, quite a few. Because I tried to remove all the technical stuff out from it, but still there is a layer of technical things which I could not have removed, you know, because it's still there is these some terms that we need to know what we are talking about. So, and that's why I hope that if you have any questions during the presentation, please stop me and ask at any time to get lost. So today we'll start with a small introduction, and then we will move through the computer vision. In particular, we go a little bit history, and then we will see OpenCV, which is the first model that we did in OpenCV. And then we will move to deep learning, which is the artificial intelligence part. We will see a little bit the theory, and then we'll see the model that we used for detecting Rust. And we'll also have we'll see the results of this project. So before problems, I have to here. So before we start, so the motivation of this project was the automatic Rust detections, and this is very important because there are what's happened normally is that people like Inspector will hire companies such as Orbital in order to fly around these drones and taking a lot of pictures and a lot of videos. But what's happened then back, they have to go through, let's say one more time, several inspectors to all these hours and hours of videos and thousands of pictures in order to detect if there is Rust and what level it is, and try to do all this work has to be done manually. So this, as you can think, it's very time expensive, and it can be very expensive in terms of time and money. So the idea is that can we create a system for automatically recognize Rust? Well, we tried. Yes, we can do that, but there are some challenges. In particular, Rust, it has not a clear shape. I mean, how you would describe Rust? Right? It's very difficult. It does, and also the color. The color can vary a lot. Between Rust, between different areas. So. And this makes it difficult to implement with standard computer vision technique. For example, if you will try to detect Rust on this needle here, you will have problems because what shape is this? I mean, and this one can be any shape. And also the color, it's very, very similar. And we know that this actually is wood and this is nail, but for a computer, it's very, very difficult to tell the difference. So. and in this project, what we did, we used the artificial intelligence, but we developed one version of using standard vision techniques. So, and you will see a little bit later what we mean by this one. So we built two different models, and then we compared the results. So, did you see the picture? Yeah, what was that? A horse? Yes, it was a horse. We can see, actually we can go through one more time. Now it's more clear, right? So it is a horse, and he was running, and it was, you can see actually a lot of details already. This image has been showed for less than a fifth of a second. And your brain was already able to pick up all the images, understand what context was it, and probably tell a lot of it, of the history of these images. Probably you can say that it's a race and so on. So this means that actually the computer vision process, we are very well trained to do this computer, like to this vision in our brain. But with computer, it's a little bit more difficult. Indeed, and that's what actually the computer vision goal is. Basically, is to replicate and exceed what is happening in the human vision by using software and hardware. That is the final goal. So, and there are, it started everything in 1966, where some people at MIT, they found this summer vision project, where they thought, where the idea was to solve this, to achieve these goals in one summer, Well, it turned out that it took a little bit longer of doing that, to finish that project, since it's still going on. And because it's extremely difficult for a computer to, let's say, detect object and correctly classify. This is something which is very, very challenging. So, when we talk about computer vision, the classic image processing, we involve pixel level operations. This means that we have the images, which is basically a sort of matrix with a lot of pixels. And we try to, let's say, cluster these pixels down, for example, trying to find the edges, and let's say, and then we change, for example, color space from RGB to HSI. So we do this, we apply all these filters in images and things like this. This is actually how computer vision is normally done today, and this is actually how it was also originally done. Lot of time ago, in order to find, for example, correlations and to find objects, we didn't have any good algorithm for doing that. So we were only relying on this sum square distance. So basically, you are taking a small subset of the image, a small region of the image. You are calculating some statistics and try to match it in other picture. But this was not working very well at all. So indeed, we had a lot of problems on doing that. Then, luckily, in 1999, it came a good algorithm, which was a scale invariant features transform, the SIFT, which was able to extract some features out from the images, like some real features, like edges and cups, and we were able to detect eyes, for example, in the faces. So, and these allowed us to start to do some real object recognition. So, I mean, you could detect faces in a different picture. So, and even if the face was a little bit tilted or if it was a different illumination, we could actually detect it. So this was a really great step forward. And then from 2012, deep learning took place. So deep learning, this does not mean that deep learning was born in 2012. This only means that we'll see what actually this date is. It's basically when deep learning, we discovered the full potential of deep learning. So, but now when you talk about a standard computer vision technique, OpenCV, there is a set of libraries which is called OpenCV, and these libraries are written in Python. They are written in C++, but they have also Python, and I think they have also Java interfaces. And this set of libraries are, let's say, they are targeting computer vision applications. So there are more than 47,000 people using it, and they include more than 2,500 algorithms that you can just use it, and also more than that, actually they are implemented, all these algorithms, and they are released under BSD license. So this means that actually you can use it and put in your commercial product and sell it. So which is very good. And the first, let's say, models that we developed was using these libraries. So basically, the solution we basically developed this first model in Python. And the only way that we had it in order to detect the rust was to look at the red components. So basically, if you don't know anything, how you will describe if there is rust or not? Well, the easiest thing is to see if there is some sort of reddish things around it, because you cannot really rely on shape, you know. So, and that's what we did. Firstly, we changed the color space from RGB to HSI. And this is basically a sort of, we changed this color space because for reducing the illumination, the impact of the illumination in the images. Basically, if you have like the same picture with different illumination, you change let's say, the quality of the red, which is there, you know. So, and if you switch to HSI, you reduce this effect, so you can tailor it better down in the red, you know, components. You can get better red components. And then we filtered out these red components based on the age. These are the value of the age we were interested to, from 0 to 11, from 175 to 180. We tailor it down, this one empirically. So we tried different numbers, and these one, they looked like were working best, you know. So, and then basically what we did, we basically counted how many red pixels there were in the picture. If the red pixels were more than 0.3%, then we said, okay, then there is rust of this image. You can think that this is very, you know, brute approach, but this was the only things that we could have done in this, under this approach, you know. So here there are some code for the one of you which are a little bit familiar with the code. Basically, we define, this is in Python. So we define some red color ranges, and then we mask it on the images. And basically here where the magic happens, the percentage where we count the non-zero, and then we say if the percentage is more than 0.3%, then it's rust. Otherwise, it's not rust. So very straightforward. Do you have any questions until now? No. Okay, good. So this was the first approach. The second approach was using artificial intelligence, and that's where things get more interesting. So before we start, we have to, you know, set up some theory because I mean, most of you will. I hope that no one was expecting today that I was showing robots and Terminator around, because there will be no such thing. So don't expect things like this when we talk about artificial intelligence, because artificial intelligence is a very overused word nowadays. They use it for almost anything, you know. So, but originally was coined for describing the tasks that were easily done by the human brain, but it was very challenging to do it in a software. So, for example, the image recognition, or the image that I showed before, your brain will actually be able to recognize these images in, I don't know, 1/5 of a second, 1/10 of a second, will already be able to do it. And while I'm speaking, people can generally understand what I say, and they can also read without any problem and understand what the reading, what a text is. So all these areas are easily performed by our brains, but it's very, very challenging. And nowadays it includes many different branches. We go from image classification to text processing or to speech recognition, for example, Siri, or I think it was Watson, the IBM first computer which was going to text processing and understanding, not only going through the word, but also understanding what the sentence was, what people were writing, you know. And this is very, very interesting. So, but those are all different branches from artificial intelligence. And we will focus on the classification task. So we'll work with images in these particular cases. So, in particular, our model is based on deep learning, which is basically a branch of the machine learning. And what it is basically try to model this high-level data, which is basically images, and we'll put these images through a set of a series of layers, which each layer includes some nonlinearity between. So, and then we'll get basically, we train these models by doing that. So basically it's 2 stages. There will be a stage where we train the model, we build the model, then we train it with a lot of data. And once that the model, we are satisfied with the model, trained enough, we can use it for doing prediction. So I told before that deep learning took place in 2012, but the theory, the mathematical theory, is actually much older. We can trace it back from 50s or 70s. So the point is that, okay, why then we took so long before actually we recognized that it was so high potential? The problem is there were 2 problems associated with it. The first problem is that we had a good theory, but we could not apply it in practice because we didn't have enough computational power. These models are extremely heavy to compute. Those are neural networks, so we need a lot of processing powers for doing it, and we didn't have back in 70s. So also another things which was stopping us from doing it from the beginning, since the beginning, was the problem of having a good data set. We will need, for training these models, we will need million and million of images, So, and it's extremely, you will need a lot of data for training these models. And that's also what was stopping. And not only do you need a lot of data, you also need to label it in the best case, where you have to say, okay, this is a dog, you need to actually put a label which say this is a picture of a dog. And you have to do it for all the million images that you are said you're doing it. So it's actually a very it's very difficult to have a good data set. And also we had some problems. We had some problems on the models itself with some things that we solved just later. And in 2012, that is an important date because there is an image challenging competition done every year. And in 2012, there was one guy, his name was Alex, where actually he outperformed all the other algorithms for image classification by using these deep learning models. So that's why 2012 was the first real case scenario where we use deep learning for doing something really useful, in image recognition. So, and this deep learning can be supervised or unsupervised. So in supervised, all the data is labeled. So this means that you have, as I told before, you have a picture of a dog, you have to write a dog. Then you have a picture of a cat, and then you write a cat, and so on. So each picture has a label, and then you feed through your model, and then your model will generate, will basically start to train, and then from time to time it will actually stop, and will cover the label, and will try to guess what it is, and then we'll say, okay, this is a cat, and then we remove the label and say, oh, it's a dog. So then I made a mistake, and then it will feed this error backwards, and then we'll update these parameters. And then it will continue this one. It will continue going through this loop again and again and again, many thousands of times, until you don't get satisfied with it. And the outputs are known because you already know that how many labels you have. So you put labels on the picture, so you already know how many these categories do you have. The other approach is using unsupervised learning, and in this case the data is not labeled. So basically in this case you will put the model, you will give a million of images, and you will tell him cluster it. And what the system will do will basically take all the data, look at it, and try to put it all the cat in one side, all the dog in the other side, and all the other animals. So we'll automatically figure out the different features, and it will try to cluster these features based on the image itself. So of course in this case the outputs are not known because the model does not know how many classes there are. It will just try to figure out by itself. And there are no loss functions or reward functions. You cannot have this feedback backwards, because it's a little bit you don't have these cost functions that you can do it because the model does not know if it's guessing correctly or not. So in this approach, in this work, we only use supervised learning. So we use labels. So we saw a little bit. Well, let's go a little bit more into practical things. We said that the deep learning is a model which uses the several layers with non-linearity. What that exactly means. So it basically means this is an example of how the layer are structured. These one we can call it neurons, and these are like connections. So basically, this is the input layer where you put your image, and your image will go through all these layers, and here you will generate a sort of prediction here. And then and then you will go back. So this is called also forward pass. So then once you did this prediction, you also generate an error, and this error will be back propagated to the input. So these W's here are the parameters that you have to set. So your task will be to find the correct combination of these parameters where your loss is minimal. That is the real task. That's everything which you really have to do. So, but what is the challenge? The challenge is that this is not a number. These are not only one numbers. You know, these are million of numbers. Each of these are actually a really huge matrix of numbers. So, and then you have to find the correct combination of it in order to give you the best prediction. So that's what actually you do. So, if you, yeah.
Do you have like images of rust in this case?
Yes. So during the training process, you will put, you will label here. You will pass image of rust, label it as a rust, and image of non-rust, label it as a non-rust, and you will go through it. And then the model will start to try to predict. And if it fails, it will go back and it will basically update these parameters all over again. You know, until you don't. This one, the model will get better and better with time. You know, every time that it loops. Hopefully, if you set everything correctly, it should get better and better in doing the predictions. So you can see here, for example, how it works. You have the different layers with some non-linearity, and this slide is very, very amazing. This is not from actually our work, because I tried to extract these features with Rust, and it doesn't come out really anything useful. So I got this image from internet where actually you can have this is for face recognition, and there are a lot of these examples. So basically, what you can see here you can see that the first layer will actually learn to detect small edges and very easy features, very simple features, the first layers. And then more you move up in the chain, more the features start to be complex, you know, until you don't reach the latest layer, which will be basically looking for this type of features like this. So, and this is actually how it works. So, and this is amazing for two reasons. The first reason is that you never tell the network to look for these features or these features or these features. The network will automatically figure out what are the features which has to extract in the image in order to do the correct recognitions. So because it will be automatically updated, the parameters you will enter in a loop where the network will automatically understand that these features is probably the best to extract in order to do a correct classification. So, and this is already amazing by itself. The second thing, which is really even more amazing, is that it's from some neurobiology studies that they did. Actually, your brain works exactly the same. So, in the meaning that your visual cortex is actually organized in layers, and the first layers, the neurons will fire up when there are like some edges and things like this, and then more you move deep into the chain, more your neurons will fire in looking at more complex images. So these are remarkable things, and actually I think the first one discovering this one in 70s or 50s, 60s, they also won a Nobel Prize in medicine. They did the experiment on cat, so it was very nice. Yeah, questions? Oh, okay. So, okay, but now we know more or less how the theory works, what is deep learning, and more or less how it works. Let's go a little bit more into the practice. I want to develop a model. Where I start? Well, people should start let's say, choosing a framework. A framework is, well, it's basically a framework where you will implement your model, where you will describe your model. And there are many frameworks available. Some of them are like Theano. There is Theano. there is Torch, there is also TensorFlow from Google. But we use the Caffe framework, and this is from Berkeley Vision and Learning Center. And this is specifically made for the image processing. So this is very tailored for image processing. And it has a very nice model zoo with a lot of pre-trained models. And you will see what these one are. Another cool thing is that these models are released under unrestricted use. So you can take these models and use it for your commercial application again without any problem. So what we did, we fine-tuned one VLC reference net. This is called the model, and it's based on AlexNet. So this was one of the first models which has been. This is actually the winner of the 2012 competition. So we why we use what means fine-tuning? Fine-tuning means that you get a model which is already pre-trained by with a lot of images, and you will just adjust it to your needs. That is the idea behind it. And this is great because it will save you a lot of time, and it will allow you to use these models even in case that you don't have enough data set. So because this model, for example, that we used, it has been pre-trained with 1.3 million images. So I mean, they had access to all these ImageNet training set, and they pre-trained these models. I mean, this process here, it took months, to do it in a extremely powerful computers. So it's not something that you do it in one day, And then this was trained to classify more than 1,000 different classes. It's a 7-layer convolutional neural network, so it consists on 7 layers. It has around 500,000 neurons, and it has more than 60 million parameters. And these are the parameters that you have to set. These parameters will be adjusted during the training, and they will find the right combination in order to give you the right prediction. So that's what it is. With fine-tuning, basically, these parameters, in general, when you start training the model from zero, you get from these parameters, they start from a sort of random. It's not actually extremely random, but it's kind of random pattern, And while you train, they will get better and better. So with pre-trained model, we actually start with a weight with these parameters, which are not random, but they already start to make sense, So they already start to look for edges and things like this, so which is extremely useful for our case. So this is the implementation, actually the implementation of the AlexNet, which was the winner of 2012, and is the one which we developed is very similar to this. And basically, you see, these are the 7 layers. You can count 1, 2, 3, 4, 5, 6, 7, and then actually there is the 8th layer, which is just a fully connected layer. And this one, basically, you will do a lot of operation, and this you can see how the dimension of the image will actually increase and shrink both in size and volume. So we modified this so in order to use that model, we had to modify the last layers, because this one was trained for recognizing 1,000 different classes. We only want to recognize 2 classes. And then we were able to, let's say, find 3,500 images of Rust and non-Rust categories. So we trained the model using these 3,500 images. We fine-tuned it. And this, it took around 2 days using these pretty powerful computers. We tried to train it on laptops, but there is no way. So you actually need what really makes the difference is the graphic card and the CUDA drivers, which allows parallel processing of the images. And we divided 80% of the image were actually used for training and 20% for validation. This because you have to divide your data set into groups, because while the model is training, from time to time you will actually stop and try to guess it, and you will use a subset of this data set in order to check if it's performing well or not well. So, and for the test we used 100 new images. which we were not, these images were not using for training or for validation. They were completely new, and we did it for testing. And on these images we actually also ran the previous model. So we compared the two models based on these 100 images.
Can I ask something?
Yeah.
Did you take these pictures of Rust yourself? 3,500 pictures, or was that in the library?
No. They are not. We got these images from real case scenarios.
Okay,
so they were actually all different pictures. And having a good data set, it's extremely important. That is, I would say, almost the most important things that you must have. Like a good data set with a good statistic independence, which try to cover all the scenario possible.
So were these images that you took with the Orbital droid?
Yes,
around?
they were from our. We got these images from different sources, but yes, it's.
So it's like relevant kind of Rust.
Yeah. It was actually from inspections. So
okay.
Yeah. So of these 100 images at which we tried to run the model, 63 were non-Rust and 37 was actually Rust pictures, and we tried to guess it to put our model. So here we marked with false positive image of non-Rust images which were classified as a Rust. So they were false positive. And then false negative image of Rust which were classified as a non-Rust. So from the algorithm. So we can see that actually the OpenCV, which was the first, we just looking at the red components, it has a lot of false positive. And why is that? It's very easy, because it can be very easily understood. Because as far as there is a guy with a red jacket walking in the picture, then it will actually be classified as a Rust, because we are looking at red components. So, and of course it has a lot of false positive. But it has very few false negative. While the deep learning model is actually, it has a 78% accuracy in both, let's say, the Rust and the non-Rust. So, but what is also cool about the deep learning model is that it gives you, let's say, a probability associated with each prediction. So this means that when you will try to guess predict an image, it will tell you, oh, I think this is Rust with a probability of 60%. Or I think this is not Rust with a probability of 95%. So this probability, if you have a probability of 60% or 55%, this is a little bit better than just random guessing, because you have only two classes, and if you just random guess, you have 50% probability. So 55 or 60 is a little bit better than guessing. So we removed all these images, and we just said, okay, I want to make sure that the model give me a probability more than 0.8%, so we discard all the, let's say, the picture where he was not completely sure about it. And actually we get an accuracy for the non-Rust around 90% and for the Rust around 79%. So we basically, for the total accuracy, we moved from 79% of OpenCV up to almost 90% with deep learning. So actually we discovered that deep learning works better in both things. Also, what is interesting to say is that we can even combine these two models in order to get better prediction. So you can, for example, since this is filtered out, it's extremely good to filter out a very low number of false negative. You could use it as a pre-screening in order to, then use it in cascade, in order to improve the probability of success. So. And here there are some examples of images which we provided. These are actually the most random images that we can have. And this is basically, you see the OpenCV only classified correctly 2/4 because it classified everything as a Rust here, basically. So this means that it's Rust because there is a lot of red here in these images. Of course, but deep learning actually correctly classified everything. All of these were correctly classified by the deep learning. So this example where the deep learning actually performed better. There are some examples where both the algorithm failed, and these are examples here. Especially, these leaves here, they look like Rust, so the algorithm were, let's say, tricked by this. And here there is Rust, but it's on the wall, on the concrete. So it's technically not Rust. It's, but I'm a little bit unsure, because if you see better the picture here, it's a little bit tricky. I mean, since both the algorithms say that this is Rust, and you know, sometimes it's also difficult for people to tell if there is Rust or not. But this one, I think there is, in all of them there is Rust, and all of them actually have been classified as Rust. So, and this is an example where the OpenCV actually performed better than deep learning. In particular, the OpenCV was able to recognize this one as a Rust, but not this one. And this one, you can see actually the color are not very, these images are not very good. And that's why actually OpenCV, I think, failed on that one. But the OpenCV, the deep learning was not able to classify this one properly. And but this one can be, let's say, improved by feeding new data, for example, for the examples of these images into the system, into the train. So, and the model then will be able also to recognize this type of Rust, like which look like this, you know. So, well, in conclusion, we had we developed two different approaches. One using a standard computer vision technique, and the other one using deep learning. And we found that actually the deep learning performed better than the standard approach. So, of course, we can combine these two models in order to improve the accuracy of all the system, the overall system. And we can. This was just a project which originally started just for as a feasibility project, but then it turned out to be actually better than what we expected, because we actually got some results. Of course, but we still had a limited amount of time, just a few weeks, you know. So if of course if this one in a larger project we can develop better models and like larger with more accuracy, and we can use a better data set in order to better train our model in a more realistic picture and things like this. So I think there is some space for improvement here. Yeah. So if we have more complete data sets, we will get better achievement. Yeah. So that was it. Thank you for your attention, and I think now if you have any questions, or welcome to ask also. Yeah.
Did you consider using spectral analysis? Would that have been possible in this case?
To use spectral, what do you exactly mean?
The one they use in astrophysics to detect what materials, what components are in
Yeah.
the star.
Yes, but you know much F36, you said the F35, you mean?
Spectral analysis.
Yes, so you want to shoot basically a light into it and see what is the absorption of the material?
Yeah.
Yeah, that is definitely. I don't know if that is. I mean, probably such system will actually be pretty expensive and very difficult to perform it. You know, with a flying drone, because you have to point it. So this will probably be easy to do. This is only possible to do it in a steady environment, but not in a so dynamic environment. So. Yeah.
So you can, if you have some places where the other doesn't work, you have a third model, you could, instead of using spectral analysis or something like that, in every picture, you use it where the other ones don't work, then you combine it. So let's say if the drone flies around and it's not able to detect something, or you get a false, maybe you get a lot of errors.
Yeah.
You could have like a third model that will go deeper into like a laser vision, you know?
Yes. The point is that this model has to be also fast in order to process all this amount of data, not in real time, but in almost real time, you know. So because this was the task. If you start to doing these very complex things, it would be easier to just go and look at image and see if there is rust, you know, or if there is something like that. And also this approach can be used for not only detecting rust, but for detecting many other features where, for example, the spectroscopy cannot be used, you know. Yeah.
Can you first look for metal structures, recognize that, and then filter out leaves and so on, and do a second recognition looking for rust on the metal structures?
Yes, I mean, it probably can be done, but it's very difficult to find and implement something, because the point is that once that you are able to detect rust, once that if you create a model which is able to detect metal, probably you are able to create a model which is also able to detect rust, you know. I mean, the point is that you will add a lot of complexity to these models, which actually, I mean, detecting metal will be as hard as detecting rust directly, you know, I think.
But you can detect the cats, for instance.
Yeah.
So once you know that something is a cat, you can start looking to see if it's a sick cat or a healthy cat and so on. So I would assume that it's easier to split the task into...
Yeah, but if I ask you to describe a cat, then it's pretty easy, so you know what features you're looking for. But if I ask you to describe a metal, it's even harder than detecting rust, you know. Like the features which they will make metal look metal, it's much more difficult to describe rather than to extract, rather than extracting the features which make a cat. You know, you can look for the head, the ear, the tail. In metal you cannot do that. You can look whatever. So you can train the deep learning in order to detect some sort of metals, for example, but
to specify, not to detect metal alone, but metal structures.
Yeah.
So because a leaf has a very curly thing, and metal are often straight or and so on.
Yeah, but if you see these images, so if you see these images here, so the difference that there is actually, this one can be just a metal sheet here, and you have like rust on top of it, and this will look like extremely similar to it, you know. So I mean, the problem of rust is that they can look whatever, you know. It can look really similar to the leaves here. Indeed, where there are some images where there are leaves near to this area, so where actually we are not fully able to understand if there are actually rust or leaves, you know. So it's a little bit more challenging, and if adding these layers,
I'd like also to mention that we had also the challenge of this is a low scope project, it's a low budget, so we actually had to match that as well. So, but what I think we've shown here that there are many possibilities. And yes, if your only interest is to see images of red apples on green balloons, the task is a lot easier. But for this thing with rust, which is kind of like, how would you actually describe rust? You know, it's not so obvious. Makes it a lot more complex. But yes, in a potential project which we already start planning, we will investigate further what are the commercial requirements to put this into commercial use, basically to wrap it into something that is useful out in the field. So yes, but yes, there are. You know, we can discuss this for weeks without reaching all the possibilities. There are many. Yeah.
Well, I'm just thinking, like, of course, you get some creative input now, so it's useful maybe to...
Yeah, thank you for that. That's good. That's what we want.
So
just to really make sure you guys understand that this is low budget. Yeah.
But you're going to continue, right?
We are.
Yeah. Because then when he said metal, I was thinking, what about infrared? Because usually, at least from concrete to metal, there will be a different reflection of infrared light. That could maybe be something we can experiment with.
Yes, but this is again, this is just if you think that this is only for rust. But the idea is that to train something. Firstly, most of the images that we have, the camera that they have on drones, it's based on let's say it's just normal cameras, and this is the first thing. So we have to work with normal cameras here. And secondly, is that this works only if you what if you want to start to see something different, you know, like different type of features, you know. In that case, may infrared camera not be the best approach anymore, you know.
No, but this is in terms of combining. Like, he probably is gonna take IR pictures anyway, so he would have two cameras, and then when he looks for rust, he would combine that information and the infrared would distinguish between metal and concrete, for example.
Yeah.
So we won't have the problem with that concrete issue.
Yeah.
We can add a little bit to that too. We are flying with infrared cameras, but again, it's like I've been saying, low hanging fruit. Like how much can we extract from electro-optic sensors without adding infrared, without scanning, and but simply detecting in by pixel-based data.
So it would be extremely cool to fly around with a full-scale laboratory, but it needs to be cost efficient, of course, and we have to worry about or think about that. This is going to be put into a commercial setting, so it needs to be cost efficient also. That's very important.
How long time did you need to train the program?
So it took for the training process it took 2 days around. So but only for the fine tuning part, which is only with 3,500 images. So it may take if you want to train the full model, it may take months. So
yeah. So if you had more time, you'd increase the accuracy. Is that what you're saying?
Yeah, probably. I mean, if you had more time, you could. Well, it's always, since it's let's say a research project, nothing is guaranteed. But I think that if you have more time, you could generate different models, more complex, with more layers. So this one will already improve you the chance of getting, let's say, a better accuracy, and also will generate a better data set. If you have a lot of time, you can really see what images we want to train the model with, So, and this one will increase the chance of having way better, let's say, predictions for.
And also, just continue there. This was originally this project was a feasibility study. Can we do it? And so it's yes, we can do it, and it's very effective, but it can of course be improved upon and with different methods and more time.
The training took a couple of days, but with how many gigaflops or teraflops? Because you need to know the power of the machine as well.
It's the power of machine is this. It's the NVIDIA GTX 980. So this.
How many gigaflops?
I think it's something around 6 gigaflops, but I'm not completely sure. You can check this one online. There are from the specification. If you go on the NVIDIA website, they have the complete specification.
Because if I use my laptop, it will probably take a month or so.
Yeah, I tried with my laptop and it doesn't work. So I mean, it will take really months. So, but what actually is interesting is to see if you are interested on the computational power more than the teraflop, because it's got to be not a very good, let's say, index anymore. There is actually on the CUDA on the NVIDIA website. They have, if you go on the CUDA drivers version, they have an index associated with each graphic card, which they measure the performance on deep learning. It's a specific index. So, and this card is actually, it's 5.2, which is the maximum basically. So it's 5.3 the maximum. This is the second best. So they have this index which measure the performance of the video card in deep learning.
Yeah, that is the training, but how long does it take to detect or?
Just a few milliseconds. Like a few milliseconds. Okay. So for doing a prediction from one image. So what is important is that images must be, let's say, resized at 256 and 256 pixels. So they are pretty relatively small images.
Let's also mention that NVIDIA has started to build GPUs for drones, for a reason, of course.
Yeah.
So you can actually put a CUDA capable GPU on the drone itself.
Yeah. And actually, we are also building some, let's say, workstations for just deep learning and training extremely complex models. So they will, I think they launched one which cost $130,000. So, yeah, just pure GPUs for parallel processing, basically.
Maybe a stupid question, but some of these pictures are really hard even for a human to detect, whether it's rust or whatever, So how would you learn and teach the computer to in order to enhance the accuracy? How would you actually
Yeah. The point
teach
is that
the computer that?
the point is that you don't tell what, the secret is, the real power of deep learning is that in respect to what was done before, was that before we were trying to say, okay, we have to tell the computer to look for these edges, and this is actually what you were doing, and you were actually hard coding that edges, and this was staying there, and then we were saying, okay, probably these edges doesn't work very well, But with deep learning, you don't do that. You actually just put a lot of images, so you, as far as you label all these images as what was it? As non-rust, for example. So, yeah, as far as you label these images as non-rust, is the model itself which will figure out that these images, this is non-rust. So it's not that you have to tell the computer, pay attention to the leaves. You will actually provide pictures with a lot of leaves, where you say these are not rust, and the computer will, the model will actually automatically figure out that this actually is non-rust. So
if you run it again, the same test, it would probably or perhaps recognize that it's not rust.
If you
run the test again.
Well, once that there are the two phases are pretty, let's say, you firstly train it and then you test it. And when you test it without retraining it, you will get always the same result.
Yeah, exactly.
So, but if you retrain it with a different set of images, you will get different results in general.
Okay.
But you will also get, each model, you will get a sort of, also the complexity of the model will play a very important role. So it's both the data set and the complexity of the model, It's like actually how you can, let's say, describe your data with a mathematical model. If you have a mathematical model which is too simple, you will never be able to describe correctly your data. And if you have a mathematical model which is too complex, then you will need a lot of data in order to, let's say, constrain it and without like avoiding overshooting and things like this. So it's basically the complexity of the model must be together with how much data you have for training it, and must go together with how difficult is your task. So these three things are bonded together.
This is actually for machine learning in general, because if you have a model that perfectly classifies your training set, that doesn't really count. That's not really what you want to do, and it's called overfitting basically. So if you have a model that overfits, you have a too high difference between the training set and real data when you test and measure the performance. So if you have a 100% hit rate on your training set, then something is wrong. Most likely, yes.
Yeah.
It should not be 100%. Yeah.
Yes.
So now you're going to add a lot of pictures with leaves into the model.
Yeah.
And see what happens next. So this is no rust, this is no rust.
Yes.
And we figure out kind of.
Yeah, that's exactly what it happens,
Only apple crisp now.
Yes.
But you will have relevant images, like a lot of images around the bridges or whatever you're going to shoot. So you can sort of, the environment is important to analyze this.
Yeah.
What could be the rust here.
Yeah.
Good.
Yeah.
So now that we ended this project, I talked a little bit about it already, but we want to put this into commercial use now. So that's what we are, and this project is ended, and now we are actually in the process of defining what do we want to do in the future. Things I mentioned in the beginning of this presentation, that this is the things we like the most to work with. This is the analytics part. This is where you are at the top of the pyramid I showed previously. And a few ending remarks.
Yeah, just say that we in Orbital we're very excited about this cooperation with BlueTech. It's been a fascinating project. We're very excited about the results, and these are indeed interesting times, and we look forward to see what happens next. And so thank you all for coming.
Thank you very much.
Thank you.